All right, momentum practice free response, set 2, number 2. I'm eating ho-hos. Because that's important for this, isn't it? All right. 2 kilogram frictionless cart. Moving at constant speed. 3 meters per second to the right. On a horizontal surface, as shown above, when it collides with a second cart of undetermined mass that is initially at rest. The force F of the collision as a function of time. Impulse. Force, time, graph, area under, impulse. Woot, woot, woot. That's what's going off on your head right now. Is shown in the graph below, where T is the instant of initial contact. As a result of the collision, the second cart acquires a speed of blah, 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 to the right. Assume that friction is negligible before, during, and after the collision. This is interesting. On initial look at, I'm not 100% sure how I'm going to incorporate this. I mean, in a way, I feel like I can just start with trying to get the lighting in here a little better. Hold on. Oh, hell. That didn't work. That didn't work at all. Well, we'll just go with that. All right, maybe we'll try this then. All right, we'll call it a day. So, what I'm not sure about is how this would work out. I'm really going to look at it first as initial momentum equals final. All right, so this is where I think we might need it, because this is an elastic, looks like at least a partially elastic collision where they bounce off of each other. So the issue is there's more variables here. So for example, in the beginning, there is just one object with momentum, and that would be the 2 kilogram cart. So its momentum, we'll say this is positive, is going to be 3 meters per second times 2 kilograms. MV, VM, whatever. Afterwards, this is where it's tricky. I got a 2 kilogram object, the first cart. Oh yeah, we got a few variables in here, so we do have some. This is where this is going to come in. With a velocity, so I'm going to call velocity of. Subscripts are always important. So we're going to call this cart 1 and cart 2, I think. Although the 2 would be confusing with the 2 kilograms. A, there we go, and cart B. That is my new names for it. So A's cart's final velocity, which I don't know. In fact, that's what they're looking. That's what they want me to find. Plus, and this is where the problem comes in, I don't know the mass of cart B. I'll even put that as B. And I do know, however, that it leaves with a velocity to the right. It has a positive 1.6 meters per second to the right. All right. I do know this is the total change. This represents the change in momentum of what? The impulse. You see, in a way, if you look at the system, it should not have a change in momentum, right? So I'm looking at this. Is this the impulse delivered to this to speed it up? But then it would also be the impulse delivered to this to slow it down, because it's the same force on both. Newton's third law, the big three. Okay, Wellborn's feet putting it together here. I swear, I'm putting it together as I go. Here's my gut feeling. This is actually the impulse on both carts. If you think about it, they both experience this force in opposite directions for the same amount of time. That force certainly acts to the right on this one and speeds it up. It will act to the left on this one. Now the question is it enough of a leftward impulse to take away this momentum and stop it? Or just slow it down a little bit? Or not only take it away, but make it go back the other way? That's what we have to find out. Okay. So what is this change in momentum? Let's look at that. So I got a triangle whose height is 10 newtons. Triangle, it's 1/2, and the base is 1 second. And the height is 10 newtons, 1/2 base times height. So I got 5 newton seconds, which is the same unit as momentum, kilogram meters per second. So this is the change in momentum for both carts. Yeah, I'm going to go with that as both. Now, this force shows just positive, but there has to be a Newton's third law component to it. So if this is just the impulse on one, it's got to be the impulse on the other. So, all right. So I'm going to go with cart A. I'm going to say that cart A has its momentum decreased by this amount because it's going to be working in the other direction, because the force obviously is going to go to the left on it. So the change in momentum for cart A is equal to A's final minus A's initial momentum. The change is impulse. That's this. I'm going to call it -5 Newton seconds, because if I make this way positive, when it hits here, the force on M is this way, positive. The Newton's third law force back this on the 2 kilogram cart is negative. So I'm going to make that negative. The final, I don't know. I just know it's still a 2 kilogram object, but I don't know that velocity. That's this right here. Minus the initial, which is 6 kilogram meters per second. So I'm going to add that 6 to both sides, and I'm going to get 1 kilogram meter per second is equal to 2 kilograms times the velocity of the A cart final. So I have a velocity of the A cart final that is 1/2 of a meter a second. So using the impulse, the change in momentum, and the final and initial momentum expressions for the cart A here, what I've called cart A, I was able to find that velocity. So I know this is 1/2. Now, if I wanted, I can come over here and I could find a couple different ways. I could find the mass. I could just plug it in here and I could find this mass. Let's see what we would do about this. I could also say that impulse, that change in impulse, that momentum for B, which would be the same as it is for A, is equal to B's final momentum minus B's initial momentum. But B's initial momentum was 0 as at rest. So its change in momentum, which was a +5 Newton seconds, is equal to the unknown mass times 1.6 meters per second, the speed that it was going afterwards. So if I divide that, (5 divided by 1.6, I get 3.125. So the mass of B is 3.125 kilograms. Now, we could do a quick check. We did all this with impulse using the graph, but if it makes sense, it should work in here, down here at the conservation of momentum. So I have this is a half a meter per second times 2. This is 3.125 times 1.6. So all of this should equal 6 kilogram meters per second. Well, let's see. Only one way to find out. No. So 2 times a half. I got that one. That's a 1. Plus, now is that plus? Yes, they're both still positive. So we're good. Plus 3.125 times 1.6. 6 even. So yes, that is a verification that what I did over here is correct, because the velocity and the mass that I found using this impulse idea fit in the conservation of momentum. So that's one of those things, I walk away from that question, I know I got every point on there. Well, unless there's some weird thing that they were looking for. But all right. Oh, well, guess what? So we did part A and B all in one, because that's kind of go-getter I am. Calculate the mass M of the second cart. We did that. Done. Check. It was the 3.125. Okay. Then it says, after the collision, the second cart eventually experiences a ramp, which it transverses with no frictional losses. The graph below. Okay, so I got my copies all jacked up. Here we go. Let's try that. The graph below shows the speed v of the second cart as a function of time for the next 5 seconds, where TO is now the instant at which the cart separates after the collision. So it goes along, and then it goes up a ramp, and therefore slows down. And then I'm assuming that it reaches the top of the ramp, which is level. All right. Calculate the acceleration of the cart at t equals 3 seconds. All right, folks, that's just the slope of this line. It's constant. Come on now. You got a speed versus time graph. That's a gimme. This is a gimme. Slope of that line. Now, let's see. What's the best way to get that? So, we know this was a speed of 1.6 coming in. And it looks like it ends up at a nice even 0.5. So, and this was at 2 seconds, we're going to say. So the 0.2 comma 1.6 is this one. And then I have the 3.5 comma 0.5. That's this point. 3.5 comma. All right. The Y's went down. Let's see, 1.6 minus 0.5, right? Make sure I get that right. 1.1, negative 1.1. The X's went up 1.5. So I have negative 1.1, my slope, is change in Y's over the change in X's. So I got 1.1 divided by 1.5. All right, so I have an acceleration that is negative 0.733 meters per second squared. Negative because the slope is definitely negative, and it shows up here as well. Calculate the distance traveled by the second cart during the 5-second interval. All right, this is just testing to see if you know what the distance, how to find the distance traveled in a speed versus time graph. Of course you do. It's the area under. All right, rate times time equals distance. This is what we want. So we got a rectangle here with a height of 1.6 and 2 seconds wide. So 1.6 times 2, and that's 3.2 meters. All right, then we got this triangle here. This has the this side is 1.1. This is 1.5. It's a triangle, so it's 1/2, 0.5, times the base, we'll call that 1.5, times the height, 0.1. Okay, let's try that again. So I get 0.5 times 1.1 times 1.5. All right, 0.825. So I get an area in here of 0.825 meters. And then we'll do this big rectangle here. That's going to be 1, 2, 3 seconds at 0.5 high. So 3 times 0.5 is 1.5 meters. So I have a total of 3.2 meters due to this section, plus this triangle, which is 0.825 meters, plus this rectangle, which is 1.5. I get it traveling 5.525 meters. That should be erased. So, straight up, they just basically are asking you to find stuff about how to read a speed versus time graph. State whether the ramp goes up or down and calculate the maximum elevation above or below the initial height. Well, if the cart slows down, the ramp's got to go up. So I'm thinking it lost. My first thought is it lost kinetic energy here, didn't it? And so whatever it lost in kinetic energy, it gained in potential. And so if I find this loss in kinetic, I will be able to find the rise in potential and use MGH to figure that out. So for example, the delta kinetic energy for the ramp equals the change, really the opposite, the change in, we'll just use magnitudes, there we go, of the gravitational potential energy. All right, so let's figure that out. Final kinetic energy was 0.5, so 1/2 times what was the mass of the cart? 3, it's not going to make a difference because it's going to divide out, but 3.125 times a velocity of 0.5 squared. The initial kinetic energy, remember I'm finding change in, was 1/2 3.125 times 1.6 squared. That equals the change in potential energy. Now, we could call, what the heck, let's say the final is just 3.125, that's m, times g, times some h. And let's make the initial 0. That way, that way he starts at a level of 0. We get to pick that, so why not? That way, when we're done, h is what we're looking for. So let's figure all this out. The 3.125s are going to go away. So I have 0.5 times 0.5 squared. That's 0.125. And then I have 0.5 times 1.6 squared. That's 1.28. And here I have GH, so I have, well, we'll be official, 9.8 times H. Here I got a drop of potential energy, of kinetic energy of so I lost 1.155 joules of kinetic energy, which means I gained that much over here. So really, I'm going to drop the negative over here because I know I lost in kinetic, but it's going to be a gain in this. So yeah, I'm just going to say their magnitudes are the same. And that's going to be 9.8 H, and we divide both sides by 9.8. And that ramp rose to a height of 0.118 meters, according to my sets of calculations there. So that's an interesting question. It's really a conservation of energy question. You have to realize, all right, it slowed down, it lost kinetic energy. Where did it go? If it's a ramp that's doing it, not friction, then it was stored in the potential energy of the ramp. So I just have to find the height of the ramp. If I assume I started at a level of 0, what's dangerous about this is this graph looks like it drops, right? But this isn't a picture of what happens. This is a graph of the speed. So that's a solid little question. All right, and I think that's it. I would say the ramp goes up. Up because speed goes down. And then do all this to find it. All right.